talk about the CEO problem today. So the so-called CEO problem is a kind of distributed source coding problem that we have one source. You can imagine that you have a CEO, basically the decoder. You have some kind of observation like this xn here, and the CEO have several managers, and each of them like observe these observations with certain noise. So these are managers, like an encoder. So what they observe instead of the original x, they observe like y1 and y2. And the goal of the CEO or the decoder is that each manager will send a compressed version of y1 and y2 to the decoder such that the CEO is able to recover the original x. And this is a kind of tough problem in general. Actually, in general, the problem is still open. I mean, if x have a general statistics. However, for the Gaussian problem, the problem is actually solved in the sense that if x is Gaussian and like the noise are also Gaussian, noise to the observation of the managers, observed by the managers. And for this special case here, I will only consider the case with only two observations or two managers here. The weight region is given below here. So if I have a fixed distortion D, that is like at the decoder, let's say we need to make sure that the observation, like x minus x hat, will have a distortion will be less than equal to D, then the rate, the required rate, will need to be at least satisfy these constraints here. And also like the D will, okay, with R1, R2, basically the weight at for encoder 1 and encoder 2, and small r1, r2 is something you can trade off here, and also D will be bigger than this expression here. Okay, this expression looks pretty ugly, but actually it's not too difficult to interpret this. You can think of like, let's say this small r1 is kind of the rate that for encoder 1 used to help encoder 2 to make encoder 2's life easier. So in the sense for this R1, what we have is, given this small R1 here, we kind of decrease the original variance of the observation sigma x squared to, let's say, similar to this expression here. And with that, then we can decrease the corresponding distortion. So instead of like log sigma x squared over D, we have like this over D, something like that. And similarly for R2 also, like R2 is basically, this small R2 is the weight for encoder 2 used to help encoder 1. And okay, for here, what I'm going to talk in this video will be just give a converse proof for this one. So basically, I will show that if the distortion is given by this guy here is bigger than this, satisfy this here, then the rate has to be bigger than this. I will leave the forward proof maybe in a later video. Basically, this proof I'm given here, following closely the book by Gamal and Kim. Okay. First, consider the sum rate bound. So we have the sum of the rate R1 and R2 will be bigger than the the entropy, the joint entropy of the message actually sent to the decoder. So, and this this joint entropy, of course, will be bigger than equal to, actually I can write bigger than or equal to the mutual information between the messages and the observation y1 and y2m. And then I can add this term here. This is basically 0 because given y1 and y2, this m1 and m2 are conditionally independent with xn. But if I add these terms here, I can merge this in the mutual information to get this mutual information here. And then I will split it in another way. First I have a xn, m1, m2, and then the second one is i1, y2n, m1, m2 given xn. Now that I can expand it like into basically 4 terms, I first expand 2 terms and then expand it again. For the 4 terms, we'll find that 2 of the terms are actually zeros, because again, like the Markov chain here. So, given, for example, for this one, I have given x and m1, then x and m1, then y1 and m2 will be conditionally independent. So anyway, so I have only 3 terms left. I'm also like for this term, I have let's see, I have y2m2 as y2m2, y2m2 given xn, and also y1n. Okay, yeah, given xn, this y1n is yeah, we don't need to care about y1n. Again, we have basically a Markov chain of xn, y1n. So therefore we have this. So now these 2 terms here, you'll rename it as nr1 and nr2. So basically, r1 is equal to I y1 and m1 given xn over n, and r2 is equal to y2 and m2 given xn over n. And because we have the data processing, we have the Markov chain here, that x hat n only is conditionally independent given m1, m2 with xn. So we can use data processing inequality that the mutual information between these 2 guys will be bigger than the mutual information between these 2. So I have that, and then like this I can revise as hxn minus hxn hat given xn, and given xn here, xn is just a constant, I can add minus xn here. Then I can remove this conditioning here. If I remove that, this will be a bigger entropy, so therefore I will have a bigger sign here because I have minus sign here. And for this hxn, I know that the mutual information is just n over 2 log 2 pi e sigma x squared. And this is actually just equal to, this is the distortion, right? So therefore, like this is just actually n over 2 log 2 pi e d. So therefore, we have this eventually. So basically, we find the first bound here for this guy here. Now let's go for the bound for R1. So we have nr1 is just bigger than equal to hm1. m1 is basically the encoder output message for encoder 1, and this is bigger than equal to hm1 given m2. So conditioning reduces entropy, and we can revise this as I m1 m. Actually, I can even write bigger than equal to, or yeah, it doesn't matter. So, and this mutual information, I can expand that. Let's see. Okay, no, I didn't expand that, but I just add this one here against HS, like what we did earlier. This is just equal to 0 because between M1 and X, given Y1 actually is conditionally independent. I can even ignore this M2 here. So therefore, I combine these two mutual information. I have this, and then I again expand in another way, and then we have this second term here, this Y1 and M, given Xm, we don't care about M2, then we can remove M2. And for this one, we can rewrite as the mutual information of Xn, M1, M2 minus mutual information between Xn and M1. And then again, like this is basically by data processing inequality, this is bigger than this. But of course, we know that these terms, the difference of these two terms originally is this one and has to be bigger than or equal to 0. So we just add this bracket per side here. Basically, when it's less than 0, we'll force it to be 0. And recall that this one is just n R1 as we defined earlier. So, and this guy, just as what we did previously, should be just equal to n over 2 log sigma x squared over d. So therefore we have, actually we are not done yet. And therefore we have this left, but we need to figure out what is this. So we can write this as hxn minus hxn given m2. The first term is easy, just equal to 1/2 log 2 pi e sigma x squared. For the second term, it will be trickier. What we are going to do is, let's just consider some another random variable xi tutor, and that this xi tutor is basically the best estimate of xi given yi, y2i. Then, because like xi given y2i is actually a Gaussian distribution with mean by this one and the variance by this one. Actually, I have another video to talk about, like for a conditional Gaussian random variable, we have mean is equal to this. Actually, this, if I have like x given y here, then the mean, assume that y and x are both 0 mean, then the mean for this condition random variable will be just say y times sigma y, or sigma xy times sigma y inverse times y times the this is basically the observed y, and the corresponding variance will be like this: sigma xx minus sigma xy sigma y inverse sigma yx. Now we just substitute into that, so we know what is sigma xy and sigma. Let's see. Sigma xx is just sigma x squared, and we have y is the best. Wait a sec. We have y. Okay, y2 basically y2 is just equal to x plus c2, right? That we described earlier. That's y2 is equal to x plus c2. So therefore, we are here. So therefore, like the expectation of y2, that's basically sigma y, maybe I should say sigma y2, but I think I omit that because it's kind of ugly, is just sigma x squared plus sigma c2 squared, right? So therefore it's this sigma y inverse is just 1 over sigma x squared, sigma c2 squared, and sigma xy is just equal to expectation xy2, and y2 is just x plus c2, and x is independent of c2, so it just have like expectation of x squared is equal to sigma x squared. So we have two of them, so we have like sigma x squared times sigma x squared, and I put 1 sigma x squared, I get this. And so anyway, so if we rewrite that, eventually we have the variance is just equal to this. Let me remove some of this. Now, because the conditional random variable x given y is given by this mean and this variance here, therefore the best estimate would be just the mean, right? So therefore, like x tilde should be just equal to this sigma x squared over sigma x squared plus sigma c2 squared times y2i. We can write xi as xi tilde plus wi here. Now then the wi is like the error, and the distribution of this wi, as we see here, is actually to be just the zero mean with variance of this conditional random variable, right? So with this variance here. And by the orthogonality principle, we have this w will be, this error will be perpendicular to the observation, basically the y here, and because it's perpendicular to y2, then it will be also perpendicular to x, because x is just a linear combination of y. And because of w is independent of y, okay, because it's Gaussian, actually when it's perpendicular, that means uncorrelated, and for Gaussian random variable, when it's uncorrelated, it's also mean independent. So w is independent of y2, and because m2 is just a function of y2, therefore w will be independent of m2 also. So therefore w will be independent of both x tilde and m2, and by that we will have w and x tilde will be conditionally independent of m. So this is actually quite easy to show. If we have w is independent of both x and m, then we basically have p xm given w is equal to p xm, right? But this is equal to p x given, let's see, m, let's say, and p, I think I don't use px given w, and p, actually I better write pm given w, and px given mw, and this is a p and px given m. Now, because m and w are also independent, this is just equal to p m, so therefore this got cancel, so we have px given mw is equal to px given m. That's exactly saying that we have a Markov chain x and w, or like x and w are conditionally independent given m. So with that, we can use the conditional entropy power inequality again, I mentioned this, I discussed this in another video about conditional entropy power inequality, entropy power inequality in general. So we have basically the entropy power is just for a vector entropy power is just 2 to the 2 hxn over n, and we have that entropy power inequality if something like xn plus yn, n is bigger than or equal to 2 to the 2 hxn plus 2 to the 2 hyn, if xn and yn are independent. And in this case, if we have conditionally independent, we'll just have condition for each of the random variable, for each of the entropy here. And now, let's see, move some more things. Now, with this conditional entropy power inequality, we can now write, let's see, yeah, we have this here, HWN given M2, because of, basically, again, W should be independent of M2, so we can remove this condition here. So we will just have this, and HW is just 1/2 log 2 pi e sigma W square, right? And we know what sigma W is this guy here. So therefore we have this. And for these other terms, I can expand this into a sum of a conditional entropy with a mutual information. And for this first term here, I can rewrite as this, and this is bigger than, okay, I have this, and then the second mutual information here, this x2 to n can be replaced by y to n here because of this Markov chain here. Basically it's a data processing inequality. And then for this guy here, I have xn, x tutor is equal to this. Therefore, like we will have like hx is basically hx tutor will be something like hy tutor plus log this guy here. So therefore we have this coming up, and then when we combine these two terms, we get this here, and then we can expand it another way, and we get these terms. We are quite familiar with this now. It's just nr2, so therefore we have this. Now for the second term here, we have two terms here. We have solved this one, and then for the second terms here, we can again expand this mutual information into a difference of two mutual information, two conditional entropy, and then for the second one, this x tutor will have a Markov chain basically. Let's see. X is independent because of here. So W is independent of M. So therefore, like given x tutor, only W will help to estimate this xy, but since M2 has nothing to do with W, so therefore this is useless, so we can remove that. Then we have this left. These things, we know that because it's actually just equal to W, and we get this one. So we have both of these. Now we can revise this guy. Oh, I know it's a lot. So remember that we started with the entropy power inequality. So we have this eventually is bigger than or equal to this guy plus these terms here. So we find this and find this. Now we're plugging in the terms here. We are plugging in this one and then plugging the other one. And then after some algebra, then we get this. Then we rearrange the terms. So these are all just algebra. Eventually we get this. So therefore we can rearrange and get like Ix and M2 is less than or equal to this guy here. And therefore, okay, we need that. Remember, we need that because of here. So now eventually we find this term and we plug that in and we got that. We got this one. And similarly, we can do the same thing for R2 and by symmetry, we can just replace sigma C2 by sigma C1 and R2 with R1, and R1 by R2 we will have the inequality for R2. Let's consider the last inequality. Because we have the Markov chain, like xn hat is conditionally independent given M1, M2, so we have the data processing inequality that the mutual information between these two guys will be bigger than or equal to mutual information between this and this. So then we can expand the second term here, the mutual information for this one, with hxn and hxn given M1, M2. Now, for the second term, we'll try to do the same thing for as before. We'll consider some x tilde that's a best estimate of x, but now we have the observation not just y1 or y2, but both y1 and y2. So by estimation theory, you know that the condition no random variable given of x given y1, y2 is given by this. That's actually a Gaussian distribution with the mean sigma xy, sigma yy inverse y1, y2. That's the observed y1, y2, and with covariance sigma xx minus sigma xy, sigma yy inverse sigma yx. Now we are different from what we have previously. We have two observations. So therefore, this sigma yy is actually a matrix, is given by this one here. So this one is actually, this sigma yy is expectation of, do it that way, expectation of y1, y2, sorry, y1, 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 y2, y2, y1, and y2, y2. And because y1 is basically equal to x plus c1, and x and c1 is independent, so therefore the variance of sigma y1 square is just equal to, the variance of y1, that is sigma y1 square, is just equal to sigma x squared plus sigma c1 square. And we previously also find, okay, sigma, I don't remember whether we did it or not, but anyway, expectation of y1, y2, we have, this is basically x plus c1, and this is x plus c2, and c1 will be independent of x and c2, so only have expectation x and x left behind. That's basically sigma x square. So therefore we have the sigma y is equal to that. So we compute the inverse for that and multiply by this guy, and eventually we'll find that this variance, now this, we again, let's call this w, will be just equal to this guy here, and this one is really something like 1 over sigma x squared plus 1 over sigma c1 square plus 1 over sigma c2 square, and inverse of that one, and also the best estimate that's for x of x given y1, y2 will be basically the mean of the conditional random variable x given y1, y2. That's equal to sigma xy times sigma y inverse times y1 and y2. And if we compute that, it will be basically, okay, that's basically this guy here. If we multiply this out, it's equal to this, and it's actually equal to sigma w squared over sigma c1 squared times y1 plus sigma w squared over sigma c2 squared times y2. Okay. Now, as before, we can write x back as like x tutor plus w, and this w have the same variance. Actually, the variance we also already mentioned that that's this variance, and this w should be independent of x tutor by orthogonality principle. It's so difficult to pronounce. So therefore, we have basically x tutor independent of w, but of course, w is also independent of y1 and y2, and therefore also the function of y1 and y2, that's m1 and m2. So therefore, like w is independent of these three terms or these three terms. And as we did before, if we have w independent of these three terms, we can write it as w is conditionally independent of x tutor given m1, m2. So with that, we can use the conditional entropy power inequality again, and we can over this term here. So we can just put it up back into that, and then we have this is bigger equal to this and this. And for the second term, again, like w is independent of m1 and m2, as we already mentioned here. So therefore, we can just remove this conditioning here. So it's just 2 to 2 hwn over n. And of course, this hwn is just n over 2 log 2 pi e sigma w squared. So we substitute that is equal to this here. And this guy we can expand into a sum of conditional entropy plus conditional mutual information. And for the first term here, know that like we have x tutor is really equal to the sum of a linear combination of y1 and y2, right, with a weight of sigma w squared over sigma c1 squared and sigma w squared over sigma c2 squared. And also, if we are given x, because we have something like this where we have x, y1, y2, and from there we construct x tutor or actually, let's see, wait a sec. Oh, actually, I don't need to care about this x tutor here, but what I mean here, I have, again, x tutor is a linear combination of y1 and y2 plus scaled by some constant here, and by the way, y1 and y2 are conditionally independent given x, so therefore we have the conditional entropy power inequality like this. And remember, like, essentially this 2 to the 2h something is if I have a 2 to the 2h, maybe this is actually sigma w square over sigma c square, right? Sigma c1 square, right? Sigma w square over sigma c1 square y1. This constant, this basically, if we think of this variable, is we have expand this variable, I mean scale this variable by this scaling factor here, right? So, and because like this entropy power 2 to the 2h something actually proportional to the variance, therefore this will be equal to 2 to the 2h y1 multiplied by, since you scale the variable by a factor of sigma w square of sigma c1 square, the variance will be scaled by the square root, so the square of that scaling factor. So we have this and that here. And let's see, this one we can expand this conditional entropy as the difference of a conditional entropy and mutual information. And again, we can use Markov chain. We remove one of this M1 and M2 here. And then we recall that this guy is actually just equal to 2 to the, let's see, this is just equal to nr1 and this is equal to nr2. So we have that. And this guy here, y1 given xn is just equal to, okay, y1 given xn will have just a variance of sigma c1 square, right? So therefore this will be just equal to 2 pi e sigma c1 square. So we have 2 pi e times sigma c1 square, so we get 1 sigma c1 square got cancelled. And similarly for this second term here also, so we have this. Now for this another term, we have this is, again, we just expand this mutual information into difference of two conditional entropy. And for this M1 and M2, you can remove that because we have x is equal to x hat x tutor plus w, and w is independent of M1 and M2. This is a similar argument as we did before. And so this term then, like xn given x tutor, is actually just similar, just 2 pi 1/2 log 2 pi e sigma w square, right? So therefore this, if we take 2 to the 2, we get this 2 pi sigma w square, and then we have only this term left. So we have both of these terms. Find we find both of these terms here. Let's see, not these two terms. Yes, should be these two terms here. Then we can now substitute that back, and we have this bigger than equal to that, and we substitute this one here into here, and this one here into here. And again, after some a little bit messy algebra, we have 2 to the 2i xn m1 m2 over n is less than equal to this guy here. Now let's see. And of course, by data processing inequality, this will be bigger than equal to this because we have the Markov chain here. And of course, this will be just equal to 1/2 log sigma x squared over d. So if we plug in everything, eventually we'll get the last inequality here. Okay, that's it for the entire converse proof. So maybe in another video I will talk about the forward proof, basically how we can achieve the to show that the weight region is actually achievable.